Good morning, everyone, and welcome to today's EcoBiz webinar. So I'm Nicole Price, and I'm a consultant with the Eco-Efficiency Group and EcoBiz. Look, as you're probably all aware, electricity use for all businesses, but in particular medium to large businesses, can be quite complex. You've got issues around demand management, power factor, quality of the grid connections, and various and changing tariff structures and network costs. So today we're really hoping to break these down and explain some of these complexities. So hopefully it will help you understand where opportunities may lie to help your business cut costs by improving how efficiently it's using its power. So Bonson, can I just get you to change to the next slide? Thank you. So before we kick off, I just want to really quickly mention the EcoBiz program. For those of you who are not familiar with it, EcoBiz is a free program. It's funded by the Queensland government and it's available to all Queensland businesses to help them reduce their energy and their water consumption, as well as reducing their waste generation. So basically it's a win-win program, and it aims to save businesses money while also helping them to reduce their impact on the environment. So I really encourage you to register, organise a free 2-hour site visit where an EcoBiz consultant can come and undertake a site assessment and suggest some really tailored recommendations to help you save. Once you've done that, there's numerous opportunities for businesses that do manage to reduce their water, energy and waste consumption by 10% to become EcoBiz partners. So, sorry, Bonson, next slide. Thank you. So it's been a incredibly successful program, as you can see just from this really quick snapshot of some of the successes. So if you haven't joined, I strongly recommend you jump online and visit our website. So today we're going to hear from Bonson Lam, who is the manager for retail pricing and tariff products at Ergon. So Bronson's had decades of experience with electricity tariffs across many different states and industries. Also joining him will be Philip Karabititos. Have I said that right, Phil? Sorry.
Karabitsios, very close.
That's it. Who is a senior energy manager advisor at Energy Queensland for nearly 10 years. So Phil primarily liaises and works with external parties and stakeholders to try and drive outcomes that benefit both customers and the network. So we've got a lot to get through today, so I'm going to hand over the reins now to Bonson and Phil. But before I do so, I just want to mention, if you've got any questions, please type them into the Q&A box on your screen, and then we're going to endeavour to answer them at the end of Bonson and Phil's presentation. So over to you, Bonson.
Thank you. Good morning, everyone. Today's webinar is about large business tariffs for regional Queensland. So a large customer is defined as somebody at the connection point is using more than 100 megawatt hours a year. Just to put that into context, an average household uses 5 megawatt hours a year. So imagine if your premise is using more than 20 houses, then chances are you would be classified as a large customer. In the regulations, you're actually called a SAC large customer, which is SAC stands for Standard Asset Class. Currently, a large customer, the most common tariffs that they're on are tariffs 44, 45, 46. Each of these tariffs have a demand component, but the demand component is currently calculated on a kW or kilowatt basis. And based on the Queensland Competition Authority, or the QCA, their draft determination for 2020-21, we will have a new option to charge on a kVA basis, initially for digital or smart metered sites. Also, if you're not on tariffs 44, 45, 46, but could be on one of these tariffs going forward, this webinar could be useful for you. For example, customers on obsolete tariffs, 20L, 22L, 62, 65, 66, or 37. If you're using more than 100 megawatt hours a year, once these tariffs expire in 2021, these three tariffs could be options for you to go into. So today we just want to talk through the change from kW to kVA calculations for demand charging and what does it mean for you. Firstly, what is peak demand? Peak demand relates to how much you're using over a half-hour period for that half-hour period. So in this example, you can see a customer between 10 a.m. and 10:30 a.m. using more energy than any other half-hour period. Currently, peak demand is calculated on a kW basis, and the amount is charged for that peak level of electricity usage over 30 minutes. It's not an instantaneous calculation, it's basically a calculation over a 30-minute period on the hour and every half hour. So to talk a little bit further about peak demand, I will introduce you to, Phil, who would talk about how this information is important and what customers can do about peak demand. Over to you, Phil.
Excellent. Thank you, Bonson. Thank you, Nicole, and good morning, all everybody online. So where I'm going to pick up here is to talk about peak demand and more specifically what it is that you can do about it. So as Bonson just spoke about there, so that your peak demand at any particular site is the half-hour average, and the maximum figure on each calendar month is what you are charged for the following month. So what in fact happens here is that you could have a period in the day or the time in your operating method where your peak demand is really high, and that's what you'll actually get charged for the whole month. Okay, so that's so this is why it's important to be aware of what your load curve looks like, so you know that if you do have any particular outlying periods of time, that you can address those. And how do you address them? Well, we can address them in the following ways. First of all, there is load shifting. So load shifting, as the name suggests, is shifting load from one time of day, particularly where it may be contributing to a significant demand peak, to another time of the day. Of course, this is conditional on the operating needs of a particular business, but is a strategy that I have seen employed many times and very successfully as well. Load shedding. Load shedding is, again, as the name suggests, turning off load where it is unnecessary for that equipment to be on at a particular time, particularly when you are getting closer to a demand threshold that you may have set for your particular business. Load shedding can be done manually, i.e. if you have a good familiarity of what it is that particular equipment around your premises may use, or it can be automated. If it is automated, they're quite often fixed into what are called peak shaving systems, which is the next one that's listed here on the slide. These peak shaving systems actively monitor where the demand is for a particular site at any particular time of day, and can work to parameters that are uploaded to the management system. Of course, the last and the classic way of helping your peak demand is efficiency. We've all seen the efficiency drives of changing out light bulbs, high bays from the old metal halide fittings to the more modern LED fittings. But of course, efficiency is an ongoing project. I've seen lights that were top of the line 3 or 4 years ago, now can be replaced with even more efficient equipment and still have really good paybacks to get for particular customers. So these are the 4 key ways that you can help reduce your peak demand. Next slide, please.
Thanks. And Phil, before I get you to talk through that, I just wanted to work through with customers who want to understand how demand is presented on their bills. So firstly, if you are on a demand tariff, if you look at the second page of your bill, and this is a Ergon Energy retail bill, you can see a column called kW. So here in this example, for that particular month, for the highest half hour, they had a chargeable demand of 38 kilowatt. So this is the actual chargeable demand component, not the actual demand. The actual demand is, for this instance, if it's tariff 44, is 68 kilowatts, but once you take off the demand threshold of 30, so the first 30 kilowatts you're not charged for it, you actually charge for 38 kilowatts. The other thing to point out in relation to your bill is trying to understand whether you're on a digital meter or not, and therefore may be charged kVA from 1st of July 2020. So in here you can see in the previous reading section, it's got a figure of 0. So digital meters are reset to 0 for each billing period. So that's another sign that you can see whether you have a digital meter or not. The other tool that we do offer for customers is energy analysis, which is a screenshot you can see on the right. And here you can see on your rightmost column and the second right column, your demand in kW and kVA. So that's basically the maximum demand for the highest half hour, both on a kW and a kVA basis. So I'm going to hand over back to Phil in relation to kVA versus kW charging.
Okay, wonderful. Thank you, Bonson. Okay, so why change the way demand is charged? So why are we shifting from kilowatt to kVA? The very simple answer to that is kVA charging is a fairer and more reflective way to charge the way that any particular customer utilizes the network than what kilowatts do. Okay, so customers who put more pressure on the network should and can be charged more. This creates an incentive for customers to reduce their maximum demand. So we want everyone to actively manage their demand. kVA also reflects the cost associated with providing sufficient network capacity to cater for the demand. And the reason is that network is built based on kVA, not kilowatts. So we build our capacities and we engineer them, and we use figures based on the kVA capacity, not the kilowatt capacity. Thank you, Bonson. Who already has kVA network and retail tariffs? Well, in Southeast Queensland, the Energex network has had them since July 2015, and in regional Queensland, so across the Ergon network, they are already in place for very large sites. So the ICC, the individual calculated sites, and the CAC sites are already on kVA tariffs. So what the QCA is proposing here in its draft determination is the next class of customer down now will also be charged kVA through the specifics that Bonson mentioned earlier. So that's coming from July 2020, and we anticipate that to be signed off on the 26th of June, so a little bit later this month. Just on that, that's okay, so just leave it there for the moment, Bonson. It's important to note that kVA charging is certainly not unique to Queensland, that most of the other jurisdictions across Australia already have got kVA charging, and also overseas, kVA charging has been implemented in many jurisdictions for many years. So this is not curve leading by any stretch of the imagination. All right, so the terms that we'll often hear when we talk about peak demand is kilowatts, kVA, and power factor is the third one. So the first one I'm going to start off with is kVA. So kVA is a term that we often hear, and it stands for kilovolt amps. Of course, in the smaller sense, just volt amps, or in the larger sense, MVA, or megavolt amps. Sometimes it's referred to as actual power. This is the measure used to build the network. So all our cables, transformers, switchgear, safety equipment, and our forecasting is all done using a kVA or MVA measurement. Okay, the network is designed using this measure, and the measure is used when working out what infrastructure needs to be in place to deliver electricity safely to the customer. Depending on the customer needs, the infrastructure requirements can and will change. That's why that's a very important line there. So because everyone that is connected to the network pays for the infrastructure in some way, we want to make sure that we are allocating the fairest cost allocation to each customer, and this is why it's so important that we're moving this way. Bonson. Thank you. So watts, kilowatts, megawatts. Okay, so this is sometimes referred to as apparent power, and we often see watts on specification plates. You can see them around any sort of sites, appliances, light bulbs, various other products. You can often turn it over, look at the specification plate, and it'll tell you how many watts or kilowatts it may need to work, or how many watts or kilowatts it can draw at its maximum. Of course, thinking of the unit of measure and how different things that seemingly do the same job can draw different amount of watts is to think of the classic incandescent light bulbs. You think of a 20-watt bulb in a room, and then you think of a 100-watt bulb globe in the room. Even though the 20-watt does a bit of a job, the 100-watt does will give out significantly brighter light, and that's because it's drawing 5 times as many watts to do that. Thank you. And power factor. Power factor is an expression of energy efficiency. It is expressed as a figure between 0 and 1, and the closer to 1 that your power factor is, the more efficiently you are using power that is delivered to your connection. Power factor is calculated by the simple formula of kilowatts divided by your kVA, your kilovolt amps. Power factor compares the real factor being consumed to the apparent power being or the demand being delivered. So again, it's an element of efficiency. Thanks, Bonson. Okay, almost time for a beer. So explaining and understanding power factor. So as we spoke about, we spoke about the formula of kilowatts over kVA equals your kVA, or your power factor. And I like to often use the beer glass example to try and demonstrate and help people understand what it is. So think of the glass as the kVA being delivered. So that is the vessel that you can fill and use with power. Now, how you use the power will depend on how much beer you get and how much foam you get to blow off the top of your beer, so to speak. So as you fill your glass, if you fill it efficiently, you will have a full glass where your kVA, your glass will equal your contents of beer, and there'll be no foam and nothing will be wasted. If you use it and fill that glass inefficiently, you'll produce more foam. The more foam that you produce means more wasted power, more of that beer that you don't get to drink. So hope that example does land with some people. Okay, another way of looking at it, and we'll start on the left-hand side here, is to look at a unpowered train carriage being drawn along a railway line by horse. Now, the true power, or the kilowatts, is what runs along the actual railway line itself. The apparent power, or the power that's actually used or required in order for that to happen, is the direction that the horse is pulling in. Now, as the horse gets more and more or less perpendicular to the railway line, the less reactive power, or the closer to unity we are, and the more efficiently the power is being used. So the more perpendicular, the higher the reactive power, the lower the power factor. Okay. So the idea is to try and get that horse to pull. If we can get it to pull right along that railway line, our true power will equal our apparent power, and our power factor will be at 1 or unity. Thank you, Bonson. Okay, so why poor power factor increases the cost of electricity supply? So I'm going to try and run through here a little example. So here we've got from the power station on the right-hand side, where we need to supply 4 buildings of power. There is a 1 MVA line that runs that can supply these 4 buildings. Thank you, Bonson. Okay, buildings 1, 2, and 3 each have a peak demand of 250 kilowatts for a total of 750 kilowatts. Building 4 is being built, and it is anticipated that it will also require 250 kilowatts of demand. Will the supply line of 1 MVA have enough capacity to service all 4 buildings? With the current information that we have, we don't know. So what we do need to factor in is, of course, each building's power factor and what kVA they're actually drawing. So we look at building 1. Building 1 has got a power factor of 0.8. Building 2 has got a power factor of 0.85. Building 3 has got a power factor of 0.9, and building 4 will have a power factor of 1, as the building design has allowed for specialized equipment that will actually deliver this. Using our formulation, we know that our kVA equals our kilowatts divided by our power factor. So therefore, we got first building 312 odd kVA, 294 and 277. 250 for the building 4, which gives us a total of about 1.13 MVA of load that network line needs to carry. Capacity is not enough, a new line is required. There are therefore new infrastructure costs for the network. Of course, the cost of that infrastructure will be borne by all customers. Okay, so this is what we're trying to avoid when we want people to actively monitor the demand and actually and use kVA as the system that we use right across the network, so we know that everyone is on a level playing field. So of course, what impacts your power factor? Thank you. Okay, or why fix poor power factor? So so power factor is of course, you know, in itself not a bad thing, but it can cause issues on sites. Of course, the first one is the cost. If you are on a kVA tariff, like many customers across Southeast Queensland already are, and some customers in regional Queensland have known for a while, is that the closer your power factor is to 1, the less impact it has on your bill. So there is a direct financial driver in order to have good power factor. The second reason is that poor power factor can increase wear and tear on equipment through the heat gains and losses as things are turned on and off within a premises. So your life of equipment can be shortened, and therefore you've got greater costs because then they're not running to maximum life. And then voltage drops. Having poor power factor on site can not only affect your site equipment, but it can also affect the local network as well. So you may be doing damage to your equipment on site, but you can also potentially be contributing to doing damage to equipment at your neighbour's site as well. So these are the key reasons why we would like to see poor power factor attended to. Thank you. Okay, so to get a little bit, I guess, more mathematical at the moment, power factor is one when the voltage and the current are in sync. So you can see there on the graph there, the blue line and the red line are syncing, as in unity, and therefore your power factor is 1. Then you got your two scenarios. Sorry, we'll just go to the next slide, please, Bonson. Okay, so then your two scenarios are, of course, when your current lags or leads the voltage. Okay, and of course that is referred to as leading or lagging power factor. Leading power factor is something that the Queensland electricity rules do not allow for. So any customer that may be leading or causing a leading power factor and feeding VARs back into the grid, okay, is not allowed under the rules. And when identified, we actively try to work with that customer to identify what the issue may be and how it can be fixed. Okay, it's and as you can see from the slide there, it's when the current peaks before the voltage peaks there. Then we have lagging power factor, which is the most common type of power factor that we see on the network, and largely what it is that customers see when their power factor is less than 1, and it happens when the current peak happens after the voltage peak. Again, typically what causes a lagging power factor is equipment that operates off a magnetic field, electric motors, transformers, arc welders, old HVAC systems, injection molding equipment, and things like that is what causes power factor to lag like that. Okay. All right. Well, excellent. Okay, so again, whether power factor is leading or lagging, there is a very specific way that it can be corrected, okay, and that's through the use of power factor correction equipment. So what power factor correction equipment does is simply brings those brings those waves back into alignment. Okay, so so the power factor can return to 1 or as close as 1 as possible for that particular site.
Thank you, Phil. So what I'd like to go through now is a step-by-step guide for power factor correction services, which each of you can potentially do for your site. The first step that you need to do is actually assess or measure your current power factor. And so therefore work out whether your site has an opportunity to improve our power factor or not. If you have a digital meter in Ergon Energy Retail, you can log on to Energy Analysis, which is an online portal open 24 hours a day, and be able to see for each of your 12 months what your maximum demand is in kW and kVA. When you divide one by the other, which you can see on the right-hand side, you can work out the power factor. So while we don't currently have power factor calculations displayed, you can quite easily work it out yourself by dividing one by the other. The only thing to note is that if you have a lot of equipment all operating at once, then your half hour when your maximum demand kVA may be slightly different to the half hour when your maximum kW demand is. But if you have only one piece of equipment, then the half hour when your maximum demand for kW and kVA will tend to be at the same time. So once you've worked out what your current power factor is, and if you see that your power factor is below 9.95 or even below 0.9, then get a specialist to come in and do a business case proposal, working out what the cost, what your investment in power factor equipment is, and working out the payback depending on the reduced kVA and the bill impact. So the most common solution, as Phil mentioned, is to install capacitor banks, which will help reduce the power factor. So step 3, once you've got the business case proposal and it does stack up, once you've implemented the correction, then actually measure the actual improvement in power factor versus what was the proposed improvement from the business case. And make sure that the actual improvement is close to your proposed improvement, and if it isn't, check in with the specialist to see what other changes needs to be done to improve power factor. Fourthly, the last step is to ensure you regularly monitor the performance and perform any maintenance if required. So just like solar or any other electrical equipment that you may have, over time the power factor may get worse. So looking at your performance every 6 or 12 months is a very helpful idea to ensure that your power factor is at the levels that you want it to be. Now what I'm going to go through is what will happen to a median customer on tariff 44 and what the QCA draft gazette is looking at in relation to their usage going forward from kilowatt to kVA basis. So in this example, you've got a monthly bill of 4,233, which is what you're currently paying, and we're using a 30-day period to calculate that usage. You also have a demand of 56 kilowatt. Given there's a 30 kilowatt threshold for tariff 44, you only actually charge for 26, being the amount in excess of your 30 kilowatt threshold. What I also do in this calculation is use different power factors from 0.7 to 0.9 to see what the impact is going on to kVA tariffs. And in order to do this, I will compare the draft 2020-21 rates which were released by the QCA, and compare it with the current rates that you're paying for 2019-20. So what you can see here, and I'll just walk through the graph on the right, is the different scenarios based on whether you're staying on kilowatt charging as well as kVA charging. So currently on the green bar, you can see on the current pricing for 2019-20, you're paying $4,233. We are seeing a reduction in the network costs. So we are expecting, based on the draft QCA determination, if you continue to be billed on a kilowatt basis, you have an 8% reduction, which is a light blue line on the right of the graph. So you would expect the 8% reduction to go from 4,233 down to 3,858 as your monthly bill. Now, if you were to go to kVA billing instead of kW billing, depending on your power factor, your monthly bill could be at different amounts. So for a customer with a high power factor, which is 0.9, your bill will actually reduce down to 3,817. On the other hand, if you have a very poor power factor of 0.7, your bill will go up a little bit to $4,256 a month, excluding GST. So what we want to do today is to get customers with poor power factors to go down towards the right-hand side of this graph so that their bill is as low as possible. Obviously, if your power factor is 0.95, you'll get an even lower bill than the 0.9, which is on this graph. Now, what we want to do is just go through a case study of a customer who have installed power factor correction equipment and walk you through their story as to what happened to them. So over to you, Phil.
Thank you very much, Bonson. So absolutely, this is a abattoir meat processing plant in a suburb of Brisbane, a fairly large operation, and they did identify, and this is going back a few years, this is one that I had my hands on. They did identify that they had poor power factor, and we also as Energex identified that they had poor power factor, and they were being impacted by the kVA charges that had already been implemented at that time. So what I did is I engaged with the plant manager and the staff to see if a solution could be found to create, like a win-win scenario, a win for the customer and a win for the network. I helped guide them through this process, and the site engaged an independent contractor to assess the power factor needs, and Energex assisted with the data and the guidance on needs requirements from the network perspective. Now, what was found is that in order to implement a solution, the cost was $185,000, which is quite significant, but I will qualify that by saying that their operation was quite large. At the time, Energex did have some incentives available, and the incentive amounted to $36,000. And then the annual maintenance cost for the whole system was $680. So you can see the ongoing cost of having one of these systems implemented is quite small. The total payback period, 1.04 years. So they've invested $185,000 of their own money, and in 12 months' time, they're effective 12 months' time, they're ahead of the game. What this installation managed to do is managed to take 900 kVA taken off the customer's peak demand, and therefore off the network as well. So that effectively gave us 1 MVA of capacity back to the network that we could allocate to other customer needs in that local area, and it also gave the customer 908 kVA that they were no longer being charged for on a monthly basis. So you can see on the pictures on the right-hand side there, if anyone's wondering what a power factor correction equipment looks like, mostly from the outside they look like big, nice orange boxes. But then you see a close-up is often a little panel that tells you where the power factor is for the particular circuit that that equipment is working on. As you can see on the example here, it's sitting on 1.00. So we've got unity power factor. This particular system as well has got an alarm system built into it, where if the power factor correction equipment stops working or trips out for any particular reason, and it can be something as simple as something to do purely electrical reasons, or it could be something like a rodent getting into the wrong spot. It trip out and it will alarm the relevant people, and they can come and reset it as quickly as possible. What happens, and what I've seen is that, and this is where sometimes with maintenance or the active management of power factor equipment can fail, is that people set it and literally forget it. They don't put an alarm system in, and when it trips out, they don't find out about it until the following month, when their peak demand is sky high again, because they've been operating without the power factor correction equipment working for them. Bonson, if we could flick to the next slide. Okay, so here on the slide, what we can see is that the purple line is the kVA, so the peaks and troughs of the peak demand, and the red line is their power factor. Okay, as we can see, quite a step change, and this is what power factor correction equipment does. When it's installed, you'll see the red line, it jumps up, and the purple line drops down. So the purple line is that's that immediate kVA saving that the power factor correction equipment facilitates for the customer, and the red line is the jump in the correction of the power factor. So jumping from that sort of 0.78 at peak, we can see that's that really low one, okay, through to mainly unity or close to unity after the power factor correction equipment has been installed. Okay, so is there any questions on the floor on the case study?
Not directly related to the case study, no.
Okay.
But in general.
In general, yes.
So is there a power factor value that indicates you really should invest in a power factor correction equipment? I guess between 0 and 1.
No, the simple answer to that is no. You can save on the charge of your kVA from anything less than unity at peak. So if you're below 1 at peak, then there can be a saving. What will dictate whether or not a particular business takes action is the return on investment. If you need to spend X to save a portion of X over 20 or 30 years, that may not be seen as a prudent investment. But if you can invest X amount, like you see in this particular case, they were sitting at 0.78, but they invested that hefty dollar fees, but they gained that back just over 12 months time. So that's can be seen as a prudent business investment for them. So it's really your business case which will drive whether or not you take action and who takes action.
Okay, because that might be related to another question that came through just about if there was any financial help for businesses to fix their power factor. So it's pretty much a business case. Is that what you're saying, Phil?
Well, yes. So there's two parts to that answer. So yes, your key driver is the business case for a particular site. Exactly right. That's going to be your key driver as to whether or not you do this. What can be what can help be part of the tipping point is to see if there are any grants available in particular areas for to help people along. What I do know is at the moment there is no talk of any broad plan to sort of facilitate these changes within the Ergon network. There are some pockets of the Ergon network that do attract some incentives, and of course customers can check those on the Ergon website as to whether or not they're within a an area that may attract an incentive, and they can obviously apply for that and put that towards their the power factor correction equipment. Alternatively, there may be other schemes that are being run by various government bodies, whether it be local, state or federal, that may also allow for investment for these purposes. But I hope that answers the question.
Yep, thanks, Phil. Do you want to leave the other questions till the end, or you keep going?
If they're related to this, I'm happy to keep going. Otherwise, we can leave them to the end.
Keep going. We'll save the other couple till the end.
Okay, wonderful. Okay, I think it's Bonson. Oh,
yeah, sure. So yeah, I can talk through it. Yeah, we have a lot of information, mainly on the Ergon Energy Network website. You can see the link there, which will help you understand a little bit more about power factors, and also we'll provide some references to other websites which could help you to understand a little bit further. So this website is just about understanding power factor and also the current regulations in relation to power factors, that some of which Phil talked to earlier on. The other references for other websites are also in here. We also have some information about areas in Ergon Energy Network that can access or be eligible for network incentives. So do go on these websites after this webinar and see if you want to invest in power factor correction equipment, whether your area is eligible or not. So just wanted to, as we go towards the end of this webinar, focus on a few take-home items that all customers with Ergon Energy retail in regional Queensland who are large customers or expanding and could be a large customer in the future should look at. So firstly, look at enrolling in energy analysis, which is a free tool that we offer to all our business customers, and it can provide you information on kilowatt and kVA demand, which would help you work out your power factor. For customers who don't have a digital meter, you can apply to upgrade to a digital meter, or potentially if you have logging equipment or have equipment that can log your demand, you can also use that to get an indication of your power factor. As mentioned earlier, sites that tend to have low power factor tend to have heavy machinery. So some examples we've put in here, like welders, furnaces, sawmills, pumps, and so forth. Particularly if you have that kind of equipment, that's definitely worth your time to have a look a little bit more into your power factor. We also have some case studies that you can look at on our website, as well as the fourth tick point, which is a website in relation to network incentives and whether your area has a network incentive. Lastly, if you do need more help, we've got some other case studies that are available on both the Ergon network and the Energix network website, as well as mentioned earlier, some of the good work that EcoBiz is doing in relation to helping customers to understand their energy usage and efficiency opportunities. So probably a good time for questions now.
Thanks, Bonson. So there's just two more. So I think it was you, Bonson, mentioned that after the correction equipment's been installed, that you need to monitor it fairly regularly. So questions come through. So if you put some new equipment in that has power factor correction in it already, does that affect your power factor correction equipment? I.e., can you have too much power factor correction?
I might get Phil to answer that.
Sure, I'll take that one, Bonson.
All right, thanks, Phil.
Okay, so the way that power factor correction equipment works is that there is a capacitance built into the cabinet itself, and they effectively engage and disengage as the capacitance is required. So if If it is oversized, so if there's too much capacitance there, it simply won't be used. So that, you know, it would be sort of a wasted investment. So yes, the answer to the question is yes, you can have too much, and that would be wasted, but that wouldn't affect, and it shouldn't, if it's set up correctly, it shouldn't affect the way that that the site operates, and it shouldn't cause any issues other than, you know, wasting a resource that you know, could be better allocated elsewhere.
Okay. And the last question is actually a question that we often get asked on our site visits, is about whether power factor correction equipment can actually reduce your energy consumption. And I guess that you were talking about possible grants. So you were talking about, you know, there might be the federal Efficient Communities grant, but power factor equipment, it's not actually about reducing your energy consumption, is it?
No, it's not about reducing consumption. Yeah. Okay, so yeah, so kilowatt hours are kilowatt hours, and they're the units that you know, that come down the line, and you'll use what you use. What it is, it's a demand reduction. So it's reducing, you know, call it the bandwidth, or the amount of space that you take up on the network to gain your kilowatts, your units of power that come to you. So that's what your power factor correction equipment helps with. So it's all got to do with the way that you interact with the network.
Yeah, great. Thanks, Phil. So I think that's it. Oh, sorry, no, I've got one last question coming in. Are there any plans to switch tariff 20 to kVA peak demand? I guess this small business.
I'll answer that. No, I'll answer that. So in the 5-year price path that Ergon Energy Network had submitted to the Australian Energy Regulator, which was just approved last week, there is no plans in the next 5 years for small customers to go on kVA tariffs. So if you're on tariff 20, which is an anytime tariff with no demand component, the plans based on the next 5 years is that you can stay on tariff 20. What I wanted to do to add to that question is that customers that are on tariff 20 will now have access to other tariffs as well. So some of them are time of use, and some of them are time of use demand tariffs. So potentially for customers who don't use a lot of energy during the peak period, which is 4 p.m. to 9 p.m. in the proposal, or can shift the demand out of that period, they could save more money going to one of these time of use or time of use demand tariffs. So the answer to the question is yes, you can keep tariff 20, but given there are new tariffs available, you should also consider whether you could save more money compared to tariff 20 by moving to a time of use energy or a time of use demand tariff.
Thanks, Bonson. Okay,
any question? You're welcome.
Any last words, Bonson and Phil?
No, thank you for your time. And
no, just I encourage everyone to do the homework.
Well,
do the homework,
yes.
and make sure that that you know, not just guess whether or not being on a kVA tariff is not going to be beneficial for you, and take the best route for your business.
Yes, I totally agree, and thank you very much, Bonson and Phil, for making some breaking down some very complicated technical information, and I think that take-home message really is that we all need to start going and looking at our bills and see exactly what is happening with our peak demand and power factor. So thanks very much, and thanks very much, listeners. Enjoy the rest of your afternoon.
Thank you all.